Moving on into section 5.2. In this one, we're going to look at some things like proving some of our trig identities. Always a good time. So, what we're looking at on this is here's just kind of their example to get us started. So they have an equation set up here, and it says sine minus cosecant equals negative cosecant times cotangent, right? So the idea is we're trying to prove that the left side is equal to the right side. That's what we're trying to prove. The strategy to doing this, and this is why I said read this, is it starts out, kind of explains what I'm going to tell you right now, but the idea is we want to look at which side seems to be more complex. That is the side that we want to start with, and we want to simplify it so that it equals the other side. So as we're doing these, typically we are not solving two sides at the same time, right? Instead, we only work on one side, and we try to get that side to match the other side. So on this one, they decided that it was best to work on the left side of the equation and try to make this look like this. This one is a little tough to determine which side is the most complex of the two. They probably would go with that left side because it has two terms instead of a single term. So that's what they went with. So down here you're seeing they took that side, and then here's what they simplified it to become. So they started with just taking the cosecant and writing that as 1 over sine. They then are working on combining these two terms together by creating common denominators. So they multiplied this one by sine over sine in order to get this. Now you can combine those together to make a single fraction because they have a common denominator, so it looks like this. We know that from our previous lesson, sine squared minus 1 is equal to negative cosine squared. On this one, they're basically separating out the cosine squared into negative cosine times cosine. So that's what you're seeing right here. They just pulled those two cosines apart so that it looks like this, because if cosine over sine is cotangent. And now this side matches the other side of the equation, and so they've proven the identity. So that's kind of the main idea on these. We're going to definitely try some of this, so fear not. So I'm going to take numbers 1 and 5 from below, and we're going to try them right here on the next page. So as I'm looking at number 1, which side looks more complex? Again, kind of debatable. Probably the left side looks more complex than the right side, but so that's what we're going to go with. So my goal is to take the left side and simplify it to make it look like the right side. So I'm going to leave the right side alone and start simplifying this as much as I can. Since I have the 1 minus cosine squared, I'm going to FOIL that. So in other words, I'm doing 1 minus cosine times 1 minus cosine. So if I were to do that, I would get 1 minus 2 cosine x plus cosine squared of x. And then I'm just going to bring down the rest of this. I'm not going to keep writing the right side of the equation, right? We're not touching that side, so we can kind of leave that one as it is and just understand that this right side of the equation just carries down since we're not changing it. As I look at these guys right here, I have a negative 2 cosine and a positive 2 cosine. So those guys are going to cancel out for me. And I am left with a 1 plus cosine squared. And again, that right side just going to carry down. So here's where it's a little tricky, because I got to figure out a way to somehow make this look like this. So I am trying to, linking back to my identity that said sine squared plus cosine squared equals 1. If I replace this guy with something from that identity, it is not going to help me get here. So this is where I have to think a little creatively on how I can make this guy look like this guy. So what I'm going to do on this one is, remember we have the identity that sine squared plus cosine squared equals 1. So I'm going to replace 1 with sine squared plus cosine squared. And I'm going to bring the rest of that down. So now it looks like this. Now I can do this guy plus this guy and say I have 2 of those. So I'm looking at sine squared of x plus 2 cosine squared of x. And there we go. Matches what we were trying to prove. So there's our proof. Let's try another one down here. So I got 1 plus tangent squared equals 1 over sine squared. Again, which one of those would be more complex? Kind of tough. I mean, this one's written as a fraction, but generally speaking, tangents are more complex than sine or cosine because tangent involves sine over cosine, right? So we know there's like multiple functions in there. So I would start by looking at the left side on this and see if I can make the left side look like the right side. And we know that 1 plus tangent squared fits directly into one of our identities that we learned in our previous lesson. So we know 1 plus tangent squared is equal to secant squared. Again, we're just going to leave that right side alone. See if I can make the left side look like the right side. So we know that secant squared is the same thing as 1 over cosine squared. And then going back to the original Pythag identity, which says sine squared plus cosine squared equals 1, within that identity, if I isolate the cosine squared, then I know that cosine squared is equal to 1 minus sine squared. So I can replace cosine squared with 1 minus sine squared. And just like that, left side equals the right side, so we're good to go. So the identities can be tough because you do have multiple options, and there can certainly be more than one way of proving an identity. So it's really just a matter of using some substitution, using your identities to figure out a path that would get you to make the two sides equal each other. So let me flip back. And so this is the page that we started on. I'm just going down below here. So here's one that was a little bit tougher that I really thought we should go through. So our goal on this one is to prove this identity that you see here. And so what we're doing on this one is we are going to leave the 1 minus cosine squared side, the right side, alone. So we're just going to carry that one down. And our goal is to clean up the left side in order to make it look like the right side. So one of the things that we're seeing on this one is none of this fits an identity, right? Because none of my quantities are squared. I don't have a tangent or a cotangent that could be simplified, so we're kind of stuck with this one being as it is. And so here's one of the tricks that we're learning that we can use to simplify in a case like this, is we can use a conjugate. Conjugates were introduced to you back in Algebra 2. We've talked a little bit about them this year. A conjugate is simply the same factor, but with the opposite sign in between. So if I have 1 plus cosine of t, the conjugate would simply be 1 minus the cosine of t. Hate when they use t's, but we'll make that work. So we are multiplying by 1 minus cosine t over 1 minus cosine t. Remember, that's just like multiplying by 1. So I'm not changing the value of anything that I have right now. I'm simply multiplying the top and the bottom by the same value just so that I can rewrite the scenario that we have. For the top part, I am going to leave those separate for now. On top, I'm looking at the sine of t times 1 minus cosine t. And on bottom, remember that when you multiply conjugates times each other, here's something we talked about before, and you guys have seen this formula before. So when I multiply conjugates times each other, I'm simply left with a squared minus b squared. So in other words, my a term is 1 and my b term is the cosine of t. So I'm going to end up with just 1 minus cosine squared of t. So there's my next line. So right off the bat, one of the things that we're going to recognize is obviously I know that 1 minus cosine squared is the same thing as sine squared. This little line here, I'm going to try to separate the lines out so we don't get confused. So I'm simply going to replace the bottom with sine squared of t. And as you're looking at that, you can see the goal is to make it look like this, right? So that's what we're shooting for. Right here, you can see that I can simplify the sine value. So I can cancel out a sine on top with a sine on bottom and just be left with 1 minus cosine of t over the sine of t. And just like that, the left side now equals the right side. So we're good to go. So again, one of the things that would probably tip you off on that one was just the idea that there really was no identity that fit this scenario, right? So I had to do something like this to make a big change because there was no direct substitution with some other identity that I could work with, like I did in the previous couple examples. Let me move on to here. All right, so there are some cases where we are going to need to work from both sides. So for this example, this one's a little challenging, so follow along on this one. What we're going to see on this one is we're starting out with an equation where both sides are really very complicated. And so it's going to be very tough as I simplify one of those sides to even make it look like the other side because they're both already pretty complex. So here's kind of what happened. So let's just say you were to look at this and you were going to say, well, I decide to simplify the left side of this equation, right? Because in a true proof, you're not supposed to simplify both, right? We're supposed to pick one, simplify that, and make it look like the other side, right? So that's the goal still. So what we're going to do on this one is say, again, I'm going to pick the left side and I'm going to simplify it. So they took the left side, looks like this, and they said, let's replace tangent squared with secant squared minus 1. Kept the bottom the same. They took the secant squared of x minus 1 and they factored it to become secant minus 1 and secant plus 1, which is the same thing as 1 plus secant. And now they look at that and they say, well, these guys can cancel, and all I am left with is the secant of x minus 1. Well, that's great, but this side, the left side, is now way simpler than the right side of the equation. So what we're seeing on this is I still need to make this look like this, right? That's still our goal. So here's the trick. The trick is we now have to make something that is simple more complex, right? Because I have to take this guy that is simple and make it look more complex, which looks like this. So how do I know what steps or what do I do? How do I apply those steps to this in order to take this simple statement and complicate it to make it look like this? So here's the trick. We're going to take this side. We are going to now simplify him to look like him, not because that's really our answer, because I can't simplify both sides. I'm only supposed to simplify one. But what we're going to see is if I can simplify this to look like this, then that will at least tell me the steps that need to be taken in order to get from here to here. So let me go through this one with you, and then we're going to do one together so you can see it. So they took the right side of the equation and simplified it. They replaced their sine squared with 1 minus cosine squared. They factored out the cosine on the bottom. They factored the top as a difference of two squares. Then they were able to cancel out the common factor right here in order to get to this stage. They then took this and broke it into two separate fractions. So they took 1 over the cosine of x minus cosine of x over cosine of x. Right? They broke it into two separate fractions because then the cosine over cosine becomes 1. And we know 1 over cosine is secant. So what we're seeing now is I now have that same result that I had on the left side. Remember, the issue in the proof is I'm not supposed to simplify both sides. But what we're seeing now is the path for how to get from here back to there. So all I have to do is, here's where I left off when I was simplifying the left side of the equation, right? I left off at secant of x minus 1. So that's this guy, which means if I want to complicate it, this would be my next step. That would be the step after that. Then this, and then eventually I'm to here as my final step. And now this side, the left side would look like the right side. So by simplifying the right side, what we're doing is we are seeing the backwards path on how to get from this all the way back to this, which is what we're trying to do. So now if we can kind of put it all together, they're now saying, here's your answer. Here's what it would look like. Is they're saying, I'm still only simplifying the left side. But as I simplify the left side, I get to this point where I'm at the secant of x minus 1. In order to make this left side look like the right side, I can now trace back through these steps in order to get there. So I know after the secant of x minus 1 would be this, and then this, and we're just retracing these steps all the way back to the beginning, and now here's our proof, right? So this is all the way from start to finish with only looking at the left side of the equation would be our answer right there. So this is a tough process. So let's go through one of these together. I can only assume you guys will be excited to do this one. So here we go. So again, I still am kind of looking at both sides look complex, but I'm still generally looking for which one looks tougher than the other one. And that's the side that I want to work with. So I'm going to take the left side of this equation and simplify it. And as I go through all of the steps, eventually these steps should equal what I'm seeing over here. So that's the goal, is to leave that right side alone and only go through steps on the left side until I get to this look right here. So first things first, we know sine squared plus cosine squared equals 1. So let's take out that cosine squared and replace it with 1 minus sine squared. On top, when I look at 1 minus sine squared, we do recognize that that is a difference of two squares, right? So it's the opposite of conjugates from what we were just talking about in a previous example. Remember, when you multiply conjugates together, you get a difference of two squares. Looks like this. So in the problem that we did before, we were here and this was the result. Well, in the problem I'm doing now, I have this, and I need to factor it to look like this. So I'm going to factor that top part and say 1 plus sine times 1 minus sine all over 1 plus sine. Right, and now as I look at that, obviously I'm seeing some factors here that could cancel, and so I'm going to be left with just 1 minus sine of x. All right, but here's the issue, and here comes kind of the trick on this problem, is obviously this is now way simpler than this. So how do I take something that is simple and make it more complex, which looks like this? So we're going to kind of cheat by finding those steps in reverse. So I'm actually going to look at this and simplify him until I'm here. So what I'm doing on this side over here is just kind of side work. This will ultimately be my answer, my complete answer. But I'm now going to do a little side work on figuring out what steps are going to need to be taken here in order to complicate it to look like this. I also just noticed that when I originally wrote this, I left out a kind of a crucial little plus sign right there. So this should say sine x plus cosine x. But again, I'm still going to now take what I have here and see what I can do to simplify it. So on this one, we actually have 4 terms. So I'm going to rewrite this. I had to take you back to one of your factoring methods that you learned how to do with 4 terms last year, something called grouping. So I'm going to reorder these a little bit. So I'm going to say 1 minus my sine of x plus cosine minus sine cosine. All right, so there's our 4 terms. So all I did was take those, rewrote them over here, but I did put them in a slightly different order. And the reason is because I was trying to get these cosines together. So you guys learned a process in Algebra 2 last year. When you have 4 terms, we can factor by what we call grouping. And grouping goes like this. I'm going to group the first 2 terms, and I'm going to group the last 2 terms. And from each group, I'm going to take out their greatest common factor. So on group number 1, there's really nothing to factor as far as a GCF, but I can just take out like a 1. So I'm going to take out a 1, which leaves me with 1 minus sine of x. On this side, I'm going to factor out cosine of x, which would leave me with 1 minus sine x. And the whole purpose of grouping was that these guys can become the same. Sorry, I should have carried that plus sign down. There's a plus sign right there. These guys are the same, so I'm actually going to factor these out as a greatest common factor. So I'm going to factor out my 1 plus sine x. And that would leave me with 1 plus cosine x. So it looks like this. So I took those 4 terms and I broke them apart into those 2 factors. And I'm going to carry down the denominator. Which looks like this. Obviously, those factors could now cancel, and I'm left with just 1 plus the sine of x, which is where I left off right here. So now real simple. How do I get from there to there? Well, all I have to do is start at 1 plus sine x and trace my steps backwards, and I got my answer. So this is where I left off. So this was my next step. So below this guy, I'm going to carry this step over. So I have 1 plus sine, 1 plus cosine. Over 1 plus cosine. So that was my next step here. What did we have before we had this? And really, what I did here was a little extra side work, just so you guys could see, excuse me, how I got these factors. So really, this little side work of the factoring process is not necessary as far as like just showing it within the steps. The idea is if I were to multiply those 2 things back together, I would get this line right here. And so I can really leave out the side factoring work that I was trying to show you for where those factors came from, and just trace it back to the original step of saying 1 minus sine cosine minus sine x plus cosine x all over 1 plus cosine. And that's it. Now the left side equals the right side, and we have our proof. And again, you could trace these steps back. Like if I wanted to look at this, so here's kind of where I left off, was how did I get from here to here? Well, obviously I just multiplied the top and the bottom by 1 plus cosine. How did I get from this step to this step? All I did was FOIL, right? So if you distribute this, you get this, and that's it. So those are the extra steps that were needed in order to get this statement right here. And so that's it as far as working on both sides of these guys. And that's going to be it for 5.2.